we're going to be finding transmitted E field now on this last part. So what we need is alpha, which is given as sigma over 2 and eta. Eta is given as eta naught over n, because we are inside of a dielectric now, inside of a material. We're not in air anymore, so we need that n variable. So we're going to have 0.4 over 2, and then we have eta, which is 377 over 9. That's going to get us 8.38. Next, we're going to need to find k, a new k for this part of the problem now. So k is going to be represented with omega over v, and v can be rewritten as c over n. So if v equals c over n, this w, we flip that, so we're going to get w over c multiplied by n. So we're going to have 10 to the 11 multiplied by 9, because square root of 81 is equal to 9. So again, n is equal to square root of e of r. We're going to have c, 3 times 10 to the 8, and that's going to give us a value of 3,000. A value of 3,000. Next, we need to find tau of perpendicular. It's given as 1 plus the gamma perpendicular, which is equal to 1 minus 0.874 equals to 0.126. So that's going to be our tau value. So next, we have everything we need for calculating the E transmitted. So the equation is going to be E t of 1 is equal to y hat of t e I of 0 e minus alpha minus 0.089x minus 0.996z. This is given from finding the r, and then we're going to have cosine 10 to 11t, because it's in phase, plus 267 plus 2988z volts per meter. We have to apply the attenuation term, the E naught, and the transmitted. This y comes from the fact that all the e's are going to be pointing in the same direction. So because it's perpendicular to the plane, and all their tangentials will be the same. So we're going to have y hat, and we're going to have 0.126 e I of there's going to be 10. The attenuation term that we found is 8.38 multiplied by all of that, duplicated there. Okay, and then we're going to have cosine, and I'm going to write 3 dots because it's all the same, volts per meter. So doing the math on it, we should get a y hat of 1.26 e to the 0.746x plus 8.35 z cosine of 10 to the 11 plus 267x plus 2988 z volts per meter. So that's going to be our ET of 1. Okay, our ET of 1 is going to be pointing out of the page, no, into the page. using our right hand rule, if K is going this way, so a thumb is going to be pointing down, diagonally down, and then our fingers are going to be going into the page here. So let's draw a bunch of fingers going into the page. So using our right hand, our palm is going to be facing this way, all right, because our fingers into the page, our thumb is going this way, our E of 2, our E of 2 is going to be pointing this way. So that's where our E of 2 is going to be going. And then let's draw. So our E of 2 is on this way. Just get these out of the way. Let's draw this a little longer. Going this way. So we're going to draw a little coordinate system here. Because with this E of 2, we're going to need to write the directions of this. Since this is only one direction, our E of T is going to need a direction the same, but this time is going to be parallel, transmitted parallel. So we have E, I have 0 still, all the same things with the attenuation term, cosine, our omega t minus kr. Again, it's going to be in volts per meter. So let's look at the angles here. So, okay, so looking at the angles here, we're going to have parallel lines here, little dotted parallel lines for a coordinate here. So there's going to be 5 degrees here. We're going to summarize it and round it up to 5 degrees just for simplicity. There's like a 90-degree triangle here, and this is going to be the not 5-degree angle, so this is going to be like the 85. That's the not the 85, yeah, the 85, that's the rest of it. And then we're going to know that this is going to be that 5.09 degrees. So that's all we really need to know this component here. So there's an x component and there's a z component. So we have a negative z and a positive x for this one. So ET of 2, we're going to have x cosine of the theta, which is 5.09, and then we're going to have an angle of negative z hat sine of 5.09. Okay, our z is in the negative direction and our x is in the positive. And then we have to multiply it by the tau of parallel, EI of 0, E 0.746 plus 8.35 z sine 10 to 11 plus 267 x plus 2988 z volts per meter. We haven't found the tau parallel. Using the equation sheet, the tau parallel should be given as eta 2 over eta 1 minus the gamma of parallel. So when you go from 1 to 2, we're going to be looking at... Okay, cut out there. So eta is going to be represented as eta naught over n. So it's going to be n2, and then we have eta naught over n1. So it's going to be 1 minus gamma parallel, and then we're going to have 377 of the medium 2, which is n2 is 9, and then this is just 377. So these two are going to cancel out, and we're going to be left with 1 over 9 of 1 minus gamma parallel. Okay, so next we're going to apply that. Gamma parallel is given as, that we found is negative 0.689. So 1 over 9, 1 plus 0.689, that's going to be equal to 0.188. That's going to be our transmitted parallel. ET of 2 is going to equal to x hat. Oh, we were written that up there. So we have that, so we just plug it in. So plugging all that in, we're going to have x cosine 5.09, z sine 5.09, 0.188 by 10, and then this stuff, we just bring it down, the attenuation term and the phase. So let's bring that all down, and then we're gonna crunch some numbers here. Okay, so let's simplify this part first. This x is going to be 0.996 minus 0.089, and then there's going to be 1.88, and then the rest are the same. So ET of 2 is going to be x hat 1.87 minus z hat 0.17, and it's going to be E, and then actually these are going to be all the same again. So it's a lot of work, but a lot of things do repeat, and if you mess up on one part, you're going to mess up on all of them. So it's important to keep track of your numbers. Okay, and that's it for finding the incident, reflected, and the transmitted.